I know. Other announcements. Probably some of you realized I slipped up and forgot to open the quiz at 8 a.m. this morning. I know. I'm sorry, everyone. I mess up too. But I extended the deadline to 11:59 p.m. You should have got an email about this. So that's open later for you guys. So you have 20 minutes to do it. Knock that out, this evening at some point if you haven't done it yet. But there's that. And then you will be able to see the answers on the quiz once everybody has completed it. So after the due date. And that's usually how I'll set things. So you will be able to see the correct answers. You'll be able to use that as a study tool for exams and stuff, but you won't be able to see those until, if you stay up till midnight tonight, you'll be able to see them after that or tomorrow. But if you have questions on any of that, shoot me an email. Question, yes? Somebody was talking?
Sorry, I didn't mean to interrupt you. Hey, it's Bailey. Sorry, I didn't mean to interrupt you.
You're good.
Is the quiz who's going to be on mastering chemistry, or is it going to be through Blackboard?
The quiz?
Yes.
Sorry, it was kind of lagging and it was breaking up your speech. It's on Blackboard. So all of our quizzes will be on Blackboard. That's the easiest way for me to go about formatting them. So yeah, we'll have homework assignments on mastering and our quizzes and exams will be on Blackboard. Does that answer it? Okay, good deal. Other announcements. So all that to say, I will get back to your emails and then, hold on, let me see what my other announcements were. Your chapter 1 homework is due Monday at midnight. So this coming Monday. After we finish lecture today, you should have all the tools and content that you need to complete that chapter 1 homework assignment. Check out the discussion boards still. I'm going to try to post another one sometime this weekend. And if I have not responded to you on discussion board, I will do that. I'm still beginning a few questions, so I'm just going to clarify one more time about the labs. If you're group A people and you did the wet lab assignment, you came into lab, your portion on Blackboard is due tomorrow by midnight, okay? You group B people, everything, both the wet lab and the dry lab is due next Friday, September 4th. So even on Blackboard, it'll say wet lab is due Friday, August 28th. That's only for group A people, okay? If you have any other questions on that, just shoot me an email. And then I think that was it. So, all right. Also, just with emails, I do get a ton of emails. And so I try to respond to them in a timely manner that I know that's important for you guys. If it ever goes like 24 hours and I haven't responded to you, just shoot me, hey, I wanted to follow up on this. Shoot me another email because that's really not likely unless it's something that I'm trying to actually go find an answer for you before I respond. So that I have the right information, but I try to be timely with those. And there are times where I'm not, forgive me, but it matters that I respond to emails quickly for you guys. So just always shoot me a follow-up email if you haven't heard back in 24 hours and I will try to get on that. Any other questions? In the meantime, we will get started. If no more.
With the homeworks, like the first homework we did, we had multiple attempts. Is that for all of the homeworks or was it just for the beginning ones?
Just for the beginning ones. Now, okay, yes and no. Essentially, you will have one main attempt, but with each individual question, you can input the answer up to 6 times. Now, you do start getting percentages of points deducted for incorrect answers. But it's not like you get one attempt for one question, then it's shut it off, move to the next question. You can try a question multiple times. But you can't attempt the whole assignment multiple times. So if you run into anything, I've had students, because you can come and go on it as well if you start it early. If you run into a problem on a question, screenshot it, send it to me. I've already had people do this. We can dialogue about that problem if you don't want to use all 6 attempts and try to get you on the right page if you're having an issue on a particular problem. So don't feel like you have to just fail that particular problem. Pause and ask me about it. And I'm more than willing to help on a particular problem so that you don't just lose all your credit for that. Make sense? Okay. I'm going to go ahead and screen share so that we can get into lecture. And I know I mentioned this as well. I have not done it yet, but by the end of the day, I will have videos uploaded on Blackboard on how to work some particular problems for that dry lab. And then any problems we don't finish in lecture today, because we didn't finish this morning, any of the complex conversion problems that we don't get to, I will also make videos of those, how to work them, but I want you to try them on your own first. And I will upload those to Blackboard by Monday. Okay. So, all right, let me share my screen. Okay, so let me pull up the chat just so that I can see it throughout lecture really quick. Okay, so remember, feel free to type in questions as you go here, and we will get into it. All right. So we, on Tuesday, just a recap of what we talked about. We went over units. We talked about why units are important, and we talked about prefixes. Okay, we introduced prefixes and how they change the quantity of a property, whatever we're measuring for a particular matter. And then we also started doing some conversions, some simple conversions, and we did scientific notation. Okay, so those were the prefixes, scientific notation, and just talking about the importance of units. And just as a reminder, why are units important? Well, you can't interpret the meaning of a number fully without a unit, and the reference points. Okay, I gave the illustration of, like, if you're gonna go on a trip somewhere and you're reading a temperature, forecast, weather forecast for that location, say it's a different country, you may not know how hot or cold that is. You may not know how to pack for that unless you have a reference point on that temperature scale that makes sense to you. Okay. So the reference points and numbers are just meaningless without them. So that's why units are important. And then we're going to work some more simple conversions, kind of where we left off Tuesday. We'll work a few problems here, and then we're going to jump into the new material. We're going to cover temperature and temperature conversions today. We're going to talk about density. We're going to talk about specific heat and energy and how to solve specific heat problems. And then we'll get into some complex conversion stuff. So that's the agenda for today. So let me go ahead and we're going to pick up with this problem for simple conversions. Okay. So let's just read this problem and then we'll work it together. It says you must transfer 0.00067 liters of a morphine solution into a plastic tube. How many microliters, and remember there's the symbol for micro, is this? So this should be a one-step conversion problem. To do this, you need a relationship between liters and microliters. Now I could scroll way up to that table and get that for us. But if you have it memorized, and micro is definitely one of the ones I want you to memorize, there's 1 million microliters in a liter. So I'm going to write that out, but I'm going to use scientific notation. So it's 10 to the 6th microliters in 1 liter. And I always encourage you, unless you're driving, to write these out with us and to do this on your own sheet of paper with us. So there's the relationship we need. We're going to start with the number given, and we want units of liters to cancel so that we end up with the correct units the question's asking for. And I'm also going to write this number here in scientific notation because that's a lot of zeros. So if we move the decimal 1, 2, 3, 4, 5 places to the right, that is 6.7 times 10 to the negative 5th liters. And that's the number I'm going to use. So 6.7 times 10 to the minus 5. Remember, this initial number needs to be a number between 1 and 10. And it is, and that unit is liters, and you can write that over 1, okay, if that helps you. And then we are going to multiply by our conversion factor, which is right here, and we want units of liters to cancel. So I'm going to put 1 liter on the bottom and 1 million microliters on the top. And now we see we have units of liters on top and on bottom, so we cross that out. And now we just have a math problem here. 6.7 times 10 to the minus 5. Why did you move it 5 and not 6 spaces? 1, 2, 3. Did I count wrong? 1, 2, 3, 4, 5. I stopped at 5 because once we had moved it 5 places, we had a base number that was between 1 and 10. If I moved it 6 places, I would have 67, and that's not a number between 1 and 10. Does that answer your question, Dallas? Okay. All right, so now we do 6.7 times 10 to the minus 5 times a million. And I believe you should have 67 microliters. Okay, is that what you guys got? Do these with me on your calculator and correct me if I'm wrong. Okay, good deal. All right, so that's that question, just a one-step conversion problem. Let's look at another one. I'm going to do the top problem, the first problem on this slide, and I'll let you attempt the next problem. I'll set you up for the next problem, and then I'll let you attempt it on your own. So let's look at this one. It's talking about miles and kilometers. It says 26.2 miles is the distance of a marathon. Any marathon runners in class with us? We respect you. We don't want to be you. 26.2 miles is the distance of a marathon. How many kilometers are in a marathon? You're back in Ferris. Okay, good. It's not on fire, I'm guessing. All right, so we need a relationship between miles and kilometers, okay? Now, did we do one? No. We could go find this. Remember those tables I was talking about on Tuesday? And I said, these are all in your textbook. I'm going to scroll up. Close your eyes if this makes your head spin. Let's go find the table for distance. So not mass. Here it is, units of length. So right here, we have a relationship. 1 mile equals 1.609 kilometers, or look up here, 0.6214 miles is a kilometer. You can use either one. I'm going to use this one down here that I circled. So 1 mile is 1.609 kilometers. So let's go back down to our problem. So 1 mile equals 1.609 km. So start with the value given, 26.2 miles. And that's over, we can write that over 1. And now we're just going to use this conversion factor. We want miles to cancel. So for every 1 mile, it's 1.609 km. Now, before we actually do the math here, I want to do what I call a concept check. Ask yourself, should my answer be a number bigger than 26.2 or smaller? Think about this. You're converting to kilometers. Which one's bigger, a mile or a kilometer?
Kilometer.
A mile is the larger distance. It takes almost 2 kilometers to equal 1 mile. You see that? So a mile is larger. So if we're converting to kilometers, it's going to take more kilometers to equal that same distance in miles, which means our value numerically should be larger. Our answer should be bigger. So that's just a way to say, okay, if I get a number smaller than 26.2, something's off. Got it? All right, so miles cancel. Anybody have our answer? How many kilometers is this?
$42.16 or 1.558.
Yeah, let's round. 42 point, just give me 2 decimals, 16. Yeah, km. Thank you, Zoe. All right, so that's that problem. Now let's set this next one up. Oh, I didn't mean to draw through it. Set this next one up, and you can attempt it on your own, okay? So it says, how many milliliters are in 2.54 gallons? Okay, so it's a little different. Gallons is not a metric unit. But we have a relationship, not directly though. We don't have a direct relationship from milliliters to gallons or gallons to milliliters. However, I bet we could find a relationship from gallons to liters. Let's go look. Sorry to scroll again. Right here, here it is. Yes, we do. Oh. So 1 gallon is this many liters, okay? Now we know how many milliliters is in a liter, but the point I wanted to make here is you can't go directly from gallons to milliliters. So let's go from gallons to liters, convert to liters first, and then we'll convert to milliliters. So the way you would set this up, here's the first relationship you would use. 1 gallon. Oh, rats, I forgot what that number was. Did anybody write it down? How many liters is 1 gallon?
3.7854.
Okay, so that's the first conversion you would use. And then we know that 1 liter equals how many milliliters?
A 1,000.
1,000. I'm gonna write 10 to the power of 3. Man, I can hear the rain outside. So this is how you would set this one up. This is the order of the relationships you would use. And you start with 2.54 gallons, convert to liters, then to milliliters. All right. Now, hopefully you guys filled this slide in. I've tried to allude to it at the very end of lecture on Tuesday. But I'm going to fill it in for you real quick, and then we're going to start some new stuff. As a reminder, to sum up everything from this point in the lecture, what we've gone over. Numbers without units, we said, are meaningless. We learned how to write and manipulate numbers in scientific notation. And we learned prefixes and their relationship to the base unit. That's what we learned. And there were 4 I asked you to memorize. So we said to memorize kilo, centi, milli, and micro. Okay. Now we're going to get into temperature. The alarms are going off again. Okay, bye. I hope y'all are okay. I don't know why the alarms keep going off. Anybody ever had your smoke alarm go off in the middle of the night?
Yes.
It's happened to
Yes.
us before. Thank the Lord my daughter was at my mom and dad's house, or she would have woke up too, at like 3 a.m. one morning. It's beautiful when that happens. Okay, temperature. We have here on this slide 3 different temperature scales. The Fahrenheit scale. Carmichael had gone off 13 times last year in one semester. Well, I would not live in that dorm again.
Amen. I was there.
Don't live in Carmichael if you can avoid it. Oh my gosh, that's ridiculous. Do people just pull it just for fun? That's awful if they do. All right, Celsius and Kelvin. These are our temperature scales. I want to point out one thing on this temperature scale before we get going with learning how to convert between these scales. So let's look at, on this scale, there's a lot of stuff pointed out, but right here we have the freezing point of water on all these scales, and then we also up here have the boiling point of water. So I want to make this a little thicker. I want to point out, when you're on the Fahrenheit scale, water freezes at 32 degrees, right? This is the temperature we were all hoping to see on the weather forecast so we get out of school, okay? So that we knew it was snow when we were growing up. They ban kitchen use after Tempe. Okay. So 32 is where it freezes. And then if you look up here, 212 is where it boils. So if we figure out the difference between these two numbers, it's 180 degrees Fahrenheit is the difference. Now let's look at the Celsius scale. Water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. That is a difference of 100. Okay. So looking at these two units of Fahrenheit, units of Celsius, if we travel 100 degrees on the Celsius scale, we have to go 180 degrees on the Fahrenheit scale. So that means Fahrenheit, units of Fahrenheit are smaller. Okay. Now let's look at the Kelvin scale. Water freezes at 273.15. And listen, those 2 decimals, 0.15, those are important. Don't ever leave those off. 270, it's not 273.0, it's 273.15. And then it boils at 373.15. That is also a difference of 100. So you notice that a move up or down on the Celsius scale is equal to a move up or down on the Kelvin scale. The units are the same size. An increase of 1 degree Celsius is also equal to an increase of 1 Kelvin. So I'm going to draw a little arrow and we'll say the units are same size. So that makes conversions between Celsius and Kelvin really easy. But it makes conversions between Fahrenheit and Celsius more difficult. So we're going to look at that in a second. All right. Also, last thing to point out, and in fact, I'm going to scroll down here to point this out. if you look at the Celsius abbreviation, Kelvin and Fahrenheit, Celsius and Kelvin, they have the little degree symbol, okay? We say degree Fahrenheit, degree Celsius, but we don't have that for Kelvin. It's just a Kelvin, okay? Don't say degree Kelvin, all right? That would be incorrect. Okay, so if we have, let's look at how to convert between temperatures. If I give you a Celsius temperature and I'm like, okay, what is that in Kelvin? You need to know how to convert. And I'm gonna ask you to memorize these two equations that we're gonna write out. But the more complicated ones below that, I'll give you for exam 1. All right, so if we have this first one I'm gonna write out on the left. If we have a temperature in Celsius and we wanna convert to Kelvin, how do we do that? Well, 0 on Celsius scale is 273.15 on Kelvin, and the units are the same size. So to convert, all we do is we take our temperature in degrees Celsius, we would plug that in, and we add 273.15, and then we get the temperature in Kelvin, okay? If you do that with 0 degrees Celsius, you get the right temp in Kelvin. All right, now let's talk about the reverse of that. If you have a temperature in Kelvin and you want to know what that is in Celsius, you just subtract off 273.15. So I cannot even tell you how many times you're going to use these two equations in this course this semester. They'll show up again and again. So please memorize those and know how to do that, okay? And sure, you could go look it up in your notes, but I just, again, for the exam, it's going to be timed. I want you to have certain things. The things I ask you to memorize, I really do want you to have those memorized so that you have them quickly and can recall them quickly for the exam, okay? All right, now how do we convert from Celsius to Fahrenheit? So this first equation over here, this one on the left is converting from degree Celsius to degree Fahrenheit. So if you have a Celsius temperature and you need it in Fahrenheit, you're going to use the one on the left. This one on the right is converting from degree Fahrenheit to degree Celsius. So don't confuse those. And it shows you what you're going to end up with on these equations. So that's how you should know which one to pick. So first off, there's a lot going on in these. You need to remember mathematical order of operations. Anybody remember that fun phrase? Please excuse my dear Aunt Sally or whatever. Mathematically, when you look at an equation, there's certain things you have to do first. And if you see parentheses in any equation, you have to do what's in the parentheses first, okay? So if you look at this equation on the left, we have in parentheses a fraction, 9/5, and there's our units, degree Fahrenheit on top, degree Celsius on bottom, times our temperature in Celsius, okay? Now I wanna make a note, here's where people commonly screw this equation all the way up and they get the wrong answer. Even though it's fairly just plug and chug, you only plug in your temperature one place. You plug your temperature, plug your Celsius temp here. Okay, you do not plug it in the fraction. Okay, these right here are just units that are attached to these numbers. Okay, but you plug your temperature in right here. All right, so don't plug it in multiple times. Don't do that. All right, I'm going to erase this so we can see clearly. So you'd plug your degree Celsius in here. The first thing you're going to do is multiply it by 9/5. Now, where in the world does 9/5 come up from? Well, up here I'll show you. Remember that if we move 180 degrees on the Fahrenheit scale, that's equivalent to a move of 100 degrees on Celsius. So we have Fahrenheit on top, Celsius on bottom. So if we write 180 over 100 and simplify this, it comes out to 9/5, okay? You can divide them by 10 and you get 18 over 10, and then divide that by 2 and you get 9 over 5. Okay, so that's where that fraction comes from, all right? Okay, once you do that, the last thing you do is you add 32 degrees Fahrenheit. And notice on this how the units cancel, okay? These units cancel right here, the Celsius, and they should, because you want units of Fahrenheit. All right, so that's the first equation. Second equation, Notice the parentheses. The parentheses tell you what to do first. So you're going to come over on the right side of this equation. You're going to plug in your temperature here. And you only plug it in one place. The other letter F's that you see are just units attached to these numbers. So you plug in your temp here, you subtract off 32, and then you multiply it, notice, by the reciprocal, 5/9. Okay? And you should never mess this up because I'm going to give you these equations on the exam, so don't mess them up. You won't. I know you won't. All right, questions on these, because now we're going to do a practice problem. And then notice, we have a way to go from Fahrenheit to Celsius and from Celsius to Kelvin, but we cannot convert directly from Fahrenheit to Kelvin. So if I give you a temperature in Fahrenheit, which is what we've done in this problem down here, and I ask for it in Kelvin, you have to first convert to Celsius. Okay? We cannot, I'm going to make a note of this, cannot convert directly to Kelvin from Fahrenheit. You first have to convert to Celsius. Okay? All right, so let's do this. We have 98.6 degree Fahrenheit. That's body temperature. What is body temperature in Celsius and Kelvin? So first we're going to go from Fahrenheit to Kelvin. All right, and so that means that we need, which equation do we need to use? The one on the right or the one on the left?
The one on the right.
One on the right. So I'm going to plug in my temperature, 98.6 degree Fahrenheit minus 32 degree Fahrenheit. And I'm going to multiply that by 5 degrees Celsius over 9 degree Fahrenheit. So first, let's do the subtraction problem. 98.6 minus 30 is 68.6. Minus 2 is 66.6 degree Fahrenheit. Now we're going to multiply this by the fraction. Okay, so somebody throw in your calculator. You need to do 5 over 9 times 66.6 degree Fahrenheit. And the units of Fahrenheit cancel out because you have it on top and on bottom. What is our answer?
37.
37.0 degree Fahrenheit. Oh, Celsius, sorry.
That's a good point. So if we accidentally put the wrong
Unit?
Unit, even though
That's
the answer's
wrong.
right,
Because units are a big deal here.
Yeah, okay.
Don't do that, Dallas. You're not going to do that.
I'm not, yeah, okay.
All right. Now we need to convert to Kelvin. So remember, let's go look at our equation. These are the ones you need to know. We're going to use this one right here. We have our Celsius temp. We're going to add 273.15. So we'll do 37 plus 273.15. And you should get 310.15. Not degree Kelvin, just Kelvin. And there it is. There's one answer. There's the other answer. Questions on that? Believe it or not, which this kind of stuff makes me laugh. My daughter just really doesn't get very sick, but there have been a few times where she spiked a fever. And for some reason, you know, when it's 2 a.m. and you're half asleep, we have a thermometer that reads different scales. And somehow I had gotten it on the Celsius scale. And for the life of me, I could not figure out how to switch it back to Fahrenheit at 2 a.m. or whatever time it was. And I'm sitting here laughing because I literally went to pull up this equation from my lecture to convert it to Fahrenheit so that I could read it. And I was like, you've got to be kidding me right now. But I got it fixed back. Okay, let's talk about energy. So all this to say, I definitely want you to be able to do a temperature conversion problem for exam 1, okay? Whether it be any direction, Fahrenheit to Celsius, back and forth, anything like this. Okay, energy. Energy, what is energy? Energy is directly related to the amount of caffeine you have every day, right? Kidding, but not kidding, kind of. Energy is the capacity to do work or supply heat. The capacity to do work or supply heat. And I would argue that is directly related to how much caffeine I have every day. We have multiple units for energy. We have the joule, this is the SI unit, the international unit, and we have the calorie, this is the metric unit. So the calorie is the one that's more common in medicine and research, but you'll also see the joule commonly reported in like publications and papers and things like that. So we need to know how to relate these two. We need a relationship between these two units because you will have to convert between them. So right here, you need to memorize this. 1 calorie is 4.184. 4.184 joules. So a calorie is bigger. Takes a little over 4 joules to get 1 calorie, okay? So anytime you're converting, your answer in joules will always be bigger than your answer in calories. Okay, your answer in kilojoules will always be bigger than your answer in kilocalories. I've also put other relationships here. We know that how many calories is in what is a kcal? Kilocalorie. Yeah, you can put K in front of any unit. It doesn't just have to be liters or grams or meters. So there's 1,000. We know what kilo stands for. There's 1,000 calories in a kilocalorie. There's 1,000 joules in a kilojoule. And this relationship for joules and calories also stands for kilocalories, okay, and kilojoules. So 1 kilocalorie is 4.184 kilojoules because you're talking on the same scale there of kilo. All right. So now we're going to introduce a new term. I wanted to talk about energy because there's units of energy in this term. We're going to talk about specific heat. So what is specific heat? Let's define it. Specific heat is the amount of energy in the form of heat required to raise the temperature of 1 gram of any substance by 1 degree Celsius. Okay, what the heck does that mean? I'm going to read it again slowly. Specific heat, it's the amount of energy or heat that we have to invest or put into something that's required to raise the temperature of 1 gram of any substance by 1 degree Celsius. So if you look at this table down here, we've got a lot of different substances listed. We've got ethanol, gold, iron, mercury, sodium. So these are all metals. And we've got water. Now look at these. Here's our specific heat values. One is in calories and one is in joules. So pay attention to which one you may need for a problem. You might need one in calories or joules. Make sure you have the right units. Which substance on here has the highest specific heat?
Water.
Water. This is a really good thing for us, okay? You're about to appreciate water even more than you did before. So water has a really high specific heat. Let's compare water to, say, ethanol. Ethanol's specific heat is a little over half that of water, okay? So if I were to ask you this, if you go into your kitchen and you get a pot of water and a pot of ethanol and you put them on your stove and you turn both burners on to the same, level of heat, which one will boil first?
The water will.
No, the water will boil second.
Ethanol.
The ethanol will boil first because it has a lower specific heat. What that means is it takes less energy, less heat to boil ethanol than it does water. Okay? Now here's why this is such a good thing. Let me give you a very practical thing here, or example. I don't know if you've lived in Arkansas your whole life, but if you've been here any amount of time, maybe longer than a year, we have cold winters and we do have hot summers. Now our bodies are roughly what % water, would you say?
67%.
Around 60, between 60 to 70% water. So quite a bit of water, okay? Because water has the highest specific heat and our bodies are not made of, say, ethanol, but they're 60 to 70% water. When our environmental conditions change, our body temperature doesn't shift with that, okay? It takes a lot of heat and a lot of energy to heat up water, okay? So our body temperature can remain relatively stable even though we're environmentally in a very hot condition or a very cold condition, okay? That's a good thing. If our bodies were 60 to 70% ethanol, our body temperature would shift a lot more dramatically with our environmental conditions than it would because it's water, okay? Does that make sense? Now look at the metals. What do you notice about their specific heat compared to relative to water?
They're lower.
They're all lower. And we know metals are conductors, right? They heat up a lot more quickly. Now you would think with as many science classes and chemistry classes I've had that I would remember this. You guys know I like to cook or bake. I've mentioned that. I'm going to give you a very real illustration of how to know that metals heat up quickly. So I grew up my whole life with a set of plastic measuring cups. Plastic, everyone. Plastic does not heat up very quickly. And we're creatures of habit, right? In my adult life, though, since I've been in the kitchen a lot and I love to acquire new kitchen tools, I asked for a set of Joanna Gaines measuring cups, and they're metal, okay? They're black and they're pretty and they're metal. My whole life, I have melted butter in a plastic measuring cup. So when I go to make cookies for the first time with my Joanna Gaines cup, I load that thing full of butter, pop it in the microwave, and I set it for over a minute. And I'm mixing everything in my bowl, and I go to the microwave and I grab it out and probably said some cuss words that I would never want my almost 2-year-old daughter. Gosh, she turns 2 tomorrow, to say, okay? Because metal gets hot when you put it in the microwave. Don't do that, everyone. All that to say, because they have a lower specific heat, it takes very little heat, very little energy for metals to get hot, okay? It takes a lot of heat, a lot of energy to heat up water. So here's the equation for specific heat. It is this, calories or joules. This is what I call your energy term. And then you have your mass. And this right here, it says degrees Celsius, but this is actually a change. Okay, this triangle is a Greek delta sign for change. In science world, anytime you see a triangle, a delta, capital delta, it means change in. So change in temp. Okay, so this is not a static temperature. This is by how much the temperature changed. So remember that. So notice there's 1, 2, 3, 4 terms in this equation. Anytime you're solving a specific heat problem, you're using algebra, you could solve for any one of those 4 terms. You just have to rearrange the equation beforehand to solve for the term you need. So we're going to actually work a practice problem. This problem on this slide is the same one down here. So I'm just going to scroll down. All right, I'm going to leave the table to where it's visible because we're going to need this in a second. Let's read our problem. How many joules, so we want to solve for joules, are required to raise the temperature of, here's our mass, 132 grams of, here's our substance, ethanol, by 10 degrees Celsius, okay? So we want to get an answer in joules. So if we're looking, I'm gonna bring this equation, I'm gonna copy it down below in an abbreviated form, and we're gonna rearrange it using rules of algebra to solve for joules. So I'm gonna abbreviate specific heat. Specific heat equals joules. We don't need calories here, so we're just using joules. So I'm gonna write J for joules over grams. I'm gonna abbreviate with a G, times your change in temperature. Now, notice the problem already gives us the temperature as the change in temperature. It says are required to raise the temp by 10 degrees. You may have some problems, and in fact, on the dry lab, there's going to be problems where it says your initial temperature was 20 degrees Celsius and the final temperature was 50 degrees Celsius. In that case, you need to calculate the change in temperature, okay? But here, you're already given the change in temperature. So just know if it gives you an initial and a final temperature, 2 temperatures, you need to find the difference, okay? And your temperature term should never be negative. Somebody asked me this, it was a great question. They said, what if your temperature is decreasing, going from say 50 degrees Celsius down to 40? Is that a negative? No, a change in temperature we always treat as an absolute value, okay? It's changing whether it's going up or going down. That is a change. So we would always plug in a positive temperature, okay? Never negative. Never plug in make a note of that. Never plug in a negative temperature. All right, so if we want to solve for the joules term right here, we need to isolate this. We need to get it by itself. How do we do that? Anybody know?
Multiply by it.
We need to move the denominator. We need to move these terms down here. Okay, so if I multiply both sides of the equation by grams times degrees Celsius, because remember, if you do something to one side of the equation, you got to do it to the other. Now look what happens. My denominator, you could write this over 1 if that helps you, but I have it on top, I have it on bottom, so they cancel out. Now I have joules by itself, so let's rewrite our equation. We're going to have grams times change in temperature times specific heat. And that is going to be equal to joules. So now we just plug everything in. We have our mass right here, 132 grams. Don't forget your units. We have our change in temperature, so times 10 degrees Celsius. We need to go look at the table. Here's ethanol, and we need to figure out, okay, which number do we need? 0.59 or 2.5? 2.5, because we want our answer in terms of joules. So we need to pick the specific heat that has joules in it, and that's 2.5. Write all the units out. You write joules on top, and let me, you probably know this, but this line right here, this per means these units are on bottom. This is a fraction, and I encourage you guys, don't write things like this all in the same line. Write them as a fraction. I'm going to write those down below. It's going to help you see which units cancel. I promise that will help you. So now let's look at what units cancel out. And this is, sorry, let me finish writing it. This is going to be equal to our answer with units of joules. So we have grams on top, grams on bottom, degrees Celsius on top, degrees Celsius on bottom, and those cancel out, we're left with joules. So now we do 132 times 10. So 1,320 times 2.5.
3,300.
3,300 joules. Okay, questions on how we did that? So here we solved for the energy term. Let me tell you, on the dry lab, there's going to be times where you have to solve for different items. You could solve for temp, change in temperature. You could solve for mass, so the grams. You could solve for the specific heat term, any one of those things. So you may have to rearrange the equation differently depending on what you're solving for, okay? So there's that. Questions on what we did? No question is a dumb question.
So you'll always provide like that type of chart there for our questions, like that shows us the.
Yeah, you do not have to memorize specific heats. If you need a specific heat, I would give that to you on an exam. I would say the specific heat of gold or blah, blah, blah is this, okay? You'll have 3 of the 4 pieces, and you need to solve for the 4th. All right. Okay, so that's specific heat, that's energy. Now we're going to talk about density. Then we're going to get into some complex conversion problems. All right. You guys may be familiar with density. If you've had any sort of science class, you've probably been introduced to the term. But density relates 2 things, mass and volume, and you can measure it for any substance, okay? So if we write the equation out, density equals mass over volume, okay? Now the units that are most commonly used here, we know mass is measured in grams, but the most common unit that we use for volume in density equations is not liters, it's milliliters. So we don't really do grams per liter. Grams per milliliter seems to be more useful. So these are our units, don't forget that. Now remember, you'll often see units of density reported in cubic distances as well. So instead of always gram per milliliter, you may see gram per cubic centimeter as well. That's very common. But know that these are the same thing, right? Because 1 milliliter is 1 cubic centimeter. So it's the same thing. All right, let's look at these 2 cylinders. Pretend these are full of air, and you can see the gas particles are the red spheres. What do you notice about these 2 cylinders? Are they the same size? They are, so they have the same volume. So which one would you say is more dense?
The one on the right.
The one on the right. This one has a higher density. Okay, why is that? It's got more particles in it, and we know density and mass are directly related. If you increase mass at a constant volume, you increase your density, okay? So anything that has more mass same size, same volume, is going to be more dense. I also wanted to show you this table here. Shows for different substances, states of matter, solid, liquids, and gases. If you look at these numbers closely, you notice for gases, these densities are pretty small. Okay, we drew pictures of solid, liquids, and gases last Thursday in that very first lecture. We drew how the molecules are arranged, if y'all remember that. And we said solids, the molecules are closely packed together, and then liquids, they're more fluid, and gases, they're further apart, and they're just zooming past each other, okay? So that's why gases tend to have a lower density, all right? And solids tend to have a higher density. Except for, there are exceptions, okay? Water, if you'll notice, as a liquid, has a density of 1. But as a solid, as ice, it's got a density, I know it's not much different, but it is lower, 0.917. And you guys are familiar with this. If you have a bottle of water and you want to get it cold really quick, or a soda, and you pop it in the freezer, the volume of that container is set, especially if it's closed. So the volume's set. And water expands, okay, as it freezes. So the volume is increasing, which lowers the density, okay? If we increase the denominator mathematically, that is going to lower the density. These are inversely related, volume and density. Density and mass are directly related. Density and volume are inversely related. All right. Let's fill in the blanks here. I want you to know, this is very important. Density is temperature dependent. And we just realized that with water. Liquid water, the temperature of liquid water is higher than the temperature of solid water. Okay? You have to lower the temperature for water to become ice. You have to raise the temperature for water to become liquid or gas. So, and the density changes, okay, because the molecules are either moving closer together or further apart. Density can also be treated as a conversion factor. Man, it is really coming down out there. Okay, how can it be treated as a conversion factor? What is a conversion factor? Remember, the definition is that it is a relationship between two units, okay? A relationship, so it is relating density. If we look at the units here, density is relating grams and milliliters, or mass and volume. So we can always use it to convert from mass to volume or vice versa. So we're actually going to work a problem in just a second. But let's look at these two slides. I have a question here. Which one is more dense? Look at the volumes, 1 liter and 1 liter. So this is at constant volume. When volume is constant, which one has more mass, the feathers or the bricks?
The bricks.
Bricks, for sure. Those are heavier. So as at constant volume, as mass increases, density increases. This is another example that they are directly proportional. All right. As mass increases, density increases at constant volume. Okay, let's look at it the other way. Which one is least dense? Look at these. What do you notice about the masses? 1 kg of flour, 1 kilogram of rice, or 1 kilogram of coins. So we have at constant mass. We're looking at a difference in volume here. Which one would you say is least dense?
The left one.
The flour, okay? So this one is least dense. It's got the largest volume. So at constant mass, as volume increases, the flour has the largest volume, density decreases. So volume and density are inversely, or I think I spelled that wrong, L-E-Y, proportional. Okay. Questions on that? Okay, that's a little bit on density. Now we're going to use density as a conversion factor. Let's look at it, what I mean by that, an example problem. It says you need 25 grams of rubbing alcohol. What volume of rubbing alcohol do I need to get? So rubbing alcohol, we know, is sold as a liquid, right? So it's easier to measure it out by volume. You can go get a syringe, you could go get a teaspoon or a tablespoon or a graduated cylinder. That's just how we like to measure volume. So what volume of rubbing alcohol should I get if the density of rubbing alcohol is 0.7855? Here's our units, gram per milliliter at room temperature. So we have a mass we want to convert to a volume. Okay, we're going from mass to volume. So we want units of milliliters, and we have a relationship. What the density means is that 0.7855 grams of rubbing alcohol equals 1 milliliter. So if I measure out 1 milliliter, or if I measure out 0.7855 grams, I'm going to have the same amount of rubbing alcohol. So start with the number we're given, 25 grams of rubbing alcohol, and we can write that over 1 if you want. Now I'm going to use this relationship, the density. This is the density. And I'm going to convert. I'm going to write it so that grams cancel. I'm using it as a conversion factor here. And I'm going to write it so that grams cancel and I'm left with milliliters. So 0.7855 grams for every 1 milliliter. I have grams on top. I have grams on bottom. They cancel. So it's just a math problem. You do 25, and remember when numbers are under on the bottom of the conversion factor, you divide by those. So 25 divided by 0.7855, what do we get?
31.83.
And the units are milliliters. Questions on what we just did? We just used density as a conversion factor. Okay, so anytime you're given if you lose connection, just know this is recorded for you. I'll post it on Blackboard. Anytime you have a problem where you're given a mass and you're asked for a volume, or vice versa, you're given a volume and you are asked for the mass, you can use density. You should use density as a conversion factor. I would make a note of that. If you're given a volume and you need to convert to mass, or you're given a mass and you need to convert to volume, density as a conversion factor, okay? Let's do one more, just for good measure here. Okay, this one's a little weird because we're given density with very unusual units. It says the average density of blood is 0.00106, and look at these units. kg, kilograms. So this is still a unit of mass, but it's not grams, per cubic centimeter, okay? We could also write that as per milliliter, because we know 1 centimeter is 1 milliliter, okay? So just go ahead and substitute that in if that helps you. If the average adult also has a volume of 5 liters of blood, what is the mass of blood in the average human body? So this is kind of a bizarre question. We want to know how much does our blood weigh. We want an answer. Our answer is going to have units of, so it's going to be some number, and the units are going to be, it says mass. It doesn't tell us what units to use, and the only units of mass we're given are right here in kilograms. So we're going to have units of kilograms per 1 average adult. So for 1 adult, how much does our blood weigh in mass? And the units we're given for mass in this problem are kilograms. Okay, now if it said, what is the mass in grams? You would need to convert, but it doesn't specify here, so we're gonna report it in kilograms, and that's acceptable. So how in the world do we do this? These are the units we need. Let's just start with the density that we're given. Okay, so 0.00106. And the units are kilogram. I'm going to go ahead and write it per milliliter because I see that I've also got units of liters, and I bet I'm going to need that density in milliliters so that I can cancel out milliliters or liters at some point. So per 1 milliliter, that's the density of blood. Now in my answer, I want kilograms on top. I have kilograms on top, so I don't want those to cancel. I want to keep those where they are. But do I want milliliters in my answer? Do I want units of milliliters in my answer? See some people going like this, some people going like this. No, we don't want milliliters. I don't see milliliters anywhere over here. So because of that, we need to cancel out milliliters. So how do we do that? Well, we have another relationship. Look right here. The average adult has a volume of 5 liters. What that means, we can write a relationship for that statement. Okay, 1 average adult equals 5 liters of blood. This is a relationship. We can use this as a conversion factor. So I'm trying to get used to reading word problems and then pulling out mathematical relationships, okay, that you can use as a conversion factor. Now the question should be, what if I'm an above average adult? What's my volume of blood? Right? Y'all are all above average. Okay, so here I still don't have milliliters, but I do have liters. Can I write a relationship from milliliters to liters? Yes, you can. 1,000 milliliters equals 1 liter. Now I'm good to go. So we want to cancel milliliters because look, over here, I have milliliters nowhere in my answer. So I got to get rid of them. So 1,000 milliliters over 1 liter. Now what happens to units of milliliters?
Cancels.
Let's keep going. Let's keep going. So we've used this conversion factor. Now let's use let's use this one right here, because I don't want liters in my answer either. I don't want units of liters. I want per average adult. So I'm going to write this next one so that I cancel liters. So 5 liters of blood per 1 average adult. And now liters will cancel as well. Wow, can y'all hear the rain?
I can see the rain.
It is coming down. I can hear it. Okay, so we've used all of our conversion factors. We've canceled out all the units, and look, the ones that don't cancel are kilograms on top, which is what I wanted, and average adult on bottom, which is what I wanted. So we do 0.00106 times 1,000 times 5. What is our answer? Oh, we'll write it up here.
5.3.
What was it?
5.3.
5.3 kilograms. That's how much your blood weighs. So roughly 5 loaves of bread. Y'all remember that? All right. So again, we use density as a conversion factor here, converting. We canceled out liter, or we canceled out the volume, okay? Now we're gonna work, let's see, we've got about 15 minutes left. So we probably have time for 1, maybe 2 conversion problems, and then anything we don't get to today, I will post a video of, and how to work it. I'll post that on Blackboard by Monday, but I want you to try to work it yourself before you just watch the video, okay? All right, let's get into this. Complex conversions. Well, what is a complex conversion problem? So far, we've been working somewhat relatively simple. If you wanted it to have said grams, could you convert that to grams first? What I would have done is I would have intervened right here. So I'm looking at the chat. Bailey had a great question. First, I would have converted to grams. Yes, I would have gone from kilograms to grams. I would have written out 1,000 grams for 1 kilogram. I would have put grams on top, kilograms on bottom, and converted to grams first. Yeah, and then I would have moved on. Yep. Okay, so we've been doing somewhat relatively simple conversions, just 1 or 2 or maybe 3 steps. Complex conversion problems are multiple steps, and then you have multiple kinds of units because you're measuring multiple things, and you might even have some unusual conversion factors, okay? I think that density up here that we used, that was an unusual conversion factor. Here's my tips for you. Do all the conversions in one problem. Here's what I mean by that. It should look somewhat like this, okay? Here's what I commonly see on exams. Here's what y'all like to do. Step number 1 is over here, and then I have to go scavenger hunt. Step number 2 is over here, crammed in the corner. And then your third conversion is actually up here. That's where the third one is. And then you write your answer down on the next page. Okay, that's like what, I'm serious, that's what students do sometimes. So keep it all linear for me. It will help you keep track of your work. and it will help me grade it. Do it all in one step. And then, what's another tip? Write down, this is a good one, write down all the conversion factors given before you start the problem. And then it's just a matter of setting it up so that the correct units cancel. Okay, so we'll practice how to identify conversion factors within a word problem and how to write them all down. Next one, a good place to start is, I'm going to circle this, usually, not always, but usually with the first number given. That's what we did up here. Our first number that we were given, that's just what we started with. And we oriented the unit so that we had kilograms on top because that's what we wanted in our answer. And then that's also leads right into my last point. Make sure you have the right units on top and bottom for your answer, okay? If we did all this work, but then kilograms was on bottom and adult was on top, we would have an inverted answer. That would not be correct. All right, so let's look at this. First problem, you get pulled over by a cop who's going to give you a ticket for going 0.028 kilometers per second in a 55-mile-per-hour speed zone. Were you speeding? And the problem gives us a conversion factor. 1.61 kilometers equals 1 mile. So we have a speed here. Our speed is in kilometers per second, and we need to convert it to miles per hour. Now, I want to point something out. We are not actually going to use this number in the problem when we're working it. This is kind of like our standard. We're going to get an answer, and then we're going to compare it to that and see if it's higher or lower. So always be looking out for, there are many times I give you a word problem like this, and I give you a standard. You don't actually use that number in your problem. You just get your answer and you compare it. Was it higher or lower to that in the end, okay? So we have kilometers per second. We want to convert to miles an hour. So we need to first convert kilometers to miles. That's step number 1. And then step number 2, we need to convert seconds to hours. Now you can first go seconds to minutes and minutes to hours if you want to, or we can do directly from seconds to hours. So let's write out our relationships. We are given the relationship between kilometers and miles right here. What is it? 1.61 km equals 1 mile. And then how many seconds is in an hour? I think we could easily come up with that. 60 seconds in a minute, 60 minutes in an hour, 60 times 60. You find that there's 3,600 seconds in 1 hour, okay? But if you want to do it in 2 steps on the time units, you're more than welcome to. So I'm going to start with my first relationship given, 0.028 km per second. Now let's double check something. When I get miles per hour, what unit is on top, what unit is on bottom? It is miles per hour. I still have units of distance on top, units of time on bottom. So I want to stay that way. And that's how I'm starting. Units of distance on top, units of time on bottom. So this is looking good. So first, it doesn't matter. I mean, you could honestly do it in either order. First, let's cancel out kilometers. So I'm going to use this relationship right here to do that. 1.61 kilometers equals 1 mile. Now units of kilometers cancel. Let's keep going. Keep going. Don't pause and get your answer here, and then just keep going all in one fluid step. That's what that first tip is alluding to. Do it all in one problem. So then we're gonna we have seconds on bottom down here. So I'm gonna use this relationship, and I'm gonna write seconds on top and 1 hour on bottom. Okay. So now seconds cancel out. And what are we left with? Miles on top, hours on bottom, which is what we want, miles per hour. So now we just do the math. 0.28 divided by 1.61 times 3,600. How fast were we going?
62, 63.
62. Are there some decimals?
Yes.
What is it?
62.60 or 61.
Okay, and that is miles per hour.
He wasn't going that fast.
Now, here's the question. Who thinks you could talk yourself out of that ticket? Uh-huh. Yeah. Fun fact, I should do a two truths and a lie on this, but here's the truth. I got like 2, maybe 3 speeding tickets my freshman year of college. I just never left on time, guys. That was my issue. Poor time management, but I've learned. I have 2 kids now, so I start getting things ready 24 hours in advance now. All right. That's one. Where are we at on time? Okay, we got time. We're going to do one more complex conversion, and then I'm going to open the floor for any questions, and we'll wrap it up for the day. All right, so hang in with me. Here's our last problem. You have a vial of a drug solution that is 65 milligrams per milliliter. Your patient, okay, you're a nurse or a doctor, whatever you want to be. Your patient needs 7 milligrams of the drug for every kilogram of body mass. The patient weighs 150 pounds. Here's our question. How many milliliters of the drug should you administer? So there's a lot of numbers. There's a lot of units in this problem. Where do we start? We're given some information here. Well, remember, one of the tips was right here. Let's just write down all our conversion factors, okay? And then we may start with the first number given. Let's see if that's the best idea. What I like to do is I like to actually put parentheses around my question. Here's my question. And what units are in my question? Milliliters. So my answer should be a number with units of milliliters only. Milliliters of drug. All right, so I need every unit to cancel except for milliliters, and I want milliliters on top. So what I like to do is I like to find any relationship that has that unit that I need in it, and it's right here. It's got milliliters in it. I'm going to start there, and I'm going to put milliliters on top. That way I know milliliters is where I want it, and then I can just start canceling out everything else. But let's write out our conversion factors first. So here's one that I circled. 65.0 milligrams of drug equals 1 milliliter. That's what that slash means, okay? We're just relating those 2 numbers. And there's an understood 1 there with the milliliters. Okay, it says your patient, here's another relationship, 7 milligrams of drug for every kilogram body mass. So don't get confused by the fact that these are both units of mass. That's okay. We're relating different things, drug to body mass, which often has to be done when you're in a medical setting, okay? You always have to take into account the size of your patient. So let me tell you, I've had 2 children, and they're going to need to give somebody that's way smaller than me or way bigger than me a different amount of, say, an anesthetic. If I don't want to feel any pain, then they would need to give me, right? So it's particular to your body mass. So I'm going to write this out. 7.00 milligrams of drug equals 1. It says for every, and that's an understood 1 kilogram of body mass. And then we also see that we have another one. The very last thing we're given is that 2.2 pounds equals 1 kilogram. All right. So I'm going to start with milliliters on top. I'm going to start with this relationship. So for every 1 milliliter, 65.0 milligrams of drug. Now, do I want milligrams in my answer? Nope. So we got to cancel that. So we've used this top one. Of these 2 conversion factors, which one will let us cancel milligrams?
The
Or 7 milligrams.
Yes. So we're going to plug, we have milligrams on bottom starting out. So I'm going to plug this in so that milligrams of drug is on top, so they cancel. Per 1 kilogram of body mass. So now look, let's go ahead and cancel these out. I got milligrams of drug on bottom, milligrams of drug on top. All right. I have right now, if I stopped, my answer would have milliliters on top and kilograms on bottom. I don't want kilograms on bottom. I just want milliliters. So I've got to cancel kilograms. So I have another relationship. I've already used this one. So we're going to use this third one, convert from kilograms to pounds. So I get rid of kilograms. So for every 1 kilogram, That is 2.2 pounds. So now kilograms cancel. And I have one more piece of information that I have not used. The weight of my patient, 150 pounds. And I can use that to cancel pounds. Now, don't be worried that there's nothing under here. Okay, you can write it over 1 if that helps you. You don't have to have anything in the denominator there. We're not relating the weight of our patient to anything. It just says your patient weighs this. All right? So now pounds cancels too. So everything cancels except for milliliters. So here's the important thing. When you go to work out this problem in your calculator, you cannot ignore this 1. You got to do 1 divided by 65. Any other time, you can ignore the 1, like when it's on the bottom over here. But when 1 is on top and it's your first number, you cannot ignore that. So to get the answer correct here, you got to do 1 divided by 65 times 7 divided by 2.2 times 150. What do we get? Why is the 1 on top? Because of the units. Okay, 1 is on top because I wanted units of milliliter on top in my answer. So I picked the conversion factor that had milliliters in it. I wrote it out as a relationship, and then I just flipped it so the milliliters on top because that's what I want my answer to have. Milliliters, units of milliliters on top. And there is an understood 1 here, okay? 65 milligrams of drug per 1 milliliter.
The answer is 7.34 milliliters.
7.34. So that is how many milliliters you would need to give this patient. Questions? These are all great questions. So look, that was a 1, 2, 3, 4-step problem. There have been exam 1 problems, which with everything being online, we're just having to have a lot more flexibility this time around, but there have been problems before that were like 10-step problems, okay? I don't want to freak you out, but you can do it. You just got to practice. Okay, any questions? Because we're pretty much at time for today's lecture. So that leaves 1, 2 problems that we didn't get to. I'll post videos on those by Monday. What did we learn today? Just real quick. 1, we learned how to convert temperatures. 2, we learned density and how to use it as a conversion factor. 3, we learned how to solve specific heat equations, how to use that equation. We learned how to solve it with the specific heat equation. And we defined it, we learned what it is. And then 4, we started working on complex conversions and how to solve those. Okay, just to summarize and put it all kind of big picture for you. That's what we did today. All right, well, I'm done. You can hop off if you need to. If you have questions, I'm going to stick around for a few minutes. Y'all have a good one and stay safe. Any questions, you guys? Okay, well, if there's no questions, I will see y'all next week. Y'all have a good weekend.